All right, here's another Eriksson exercise, and this time I've actually got my microphone going, so that means that the voice quality is not going to be horrific. So, we want to prove that A is positive definite. And remember, what is A? A is basically, you can, this is how we define A. A is defined to be this matrix, where the ij entry is given by this integral, where the phi i's and phi j's, those are the basis of hat functions that we're using. Okay, so anyways, we want to prove that A is positive definite, and we want to use this fact here. And once you know this fact, it's pretty much immediate, because what does it mean? A is positive definite if for every single vector n, the inner product of basically the bilinear form that you get from the matrix A, if you take that, but if you take this inner, well, it's not an inner product, it's a bilinear form. If you compose two elements with any two vectors with each other, it'll give you a value that's greater than or equal to 0. Did I do this correctly? Okay, so what have I done here? I've proven that A is positive semi-definite. Okay, so that's not enough. Okay, so I messed this up. That's upsetting. So if this holds, then it's positive semi-definite. For it to be positive definite, you need to confirm that this equation holds for every single non-zero vector eta. Oh man, that's really upsetting. I've already turned in this assignment. Ugh. Oh well. So anyways, VH is defined by this. Okay, so how would you go about doing this problem? Basically what you'd start with is, this is really useful here, because this gives you a way of formulating this inner product. And so what do? You sort of start with this, and like, just looking at this equation, this isn't obvious to me at all that you would get these two things to be equal. But what you can do is you start with the right-hand side, and you just expand it out and see if you can get something that looks like the left-hand side. So that's exactly what we do. We're going to use the form of A and the fact that A is symmetric. So we start with this integral. V is defined here, so we'll write that out. Differentiation can be brought inside, so we just bring the phi I prime there. Now, if you look at this sum, and if you think about if you were to square the sum, then for each I you would end up you take these eta I phi I primes for I equals 1 to m, and for each of those, for each eta I phi I prime, if you consider any other eta j phi prime j, then there will be one term which is the product of those two. So you can write this, this square here can be written as this double sum, where you're summing from I equals 1 to m and j equals 1 to m of just, well, you take eta I times phi I prime and then multiply by eta j times phi j prime, and you just move the etas and the phi's together. And then what you do is you bring this integral inside here, past the sum and past the constants, and you get this thing, but this thing is AJI, which is the same thing as AIJ, and you bring this eta I out front here as well to get this thing. And then from here, I think the easiest way to get from here to the final thing is to actually start here, write it out using eta I's and AIJ's, and actually sort of expand this out, and you'll see that you get the same thing as here. Because this eta transpose, that's just this vector here. And then if you multiply eta, if you take the product A times eta, you'll see that the matrix you get is just a a matrix of, it's a m by 1 matrix, so you've got m columns, or m rows in one column, and the indices are given by this, these sums. And then if you were to take this matrix and multiply it by this matrix, you would just get this. And so that's how these things are all equal. So regardless of our choice of eta, vi prime squared is greater than 0, so this is that. And then I'm going to explain this part next, and then I'm going to go back and prove that it's actually positive definite, and I'm going to try to do that on the fly. But basically, I feel like this is a thing that you see a lot, this sort of, like bringing this integral inside the sums. And there's actually a way you sort of can technically prove that, because you can't do that for any like continuous functions in general. It turns out in order to do that, that comes down to measure theory, and you need to use some measure theoretic facts to actually rigorously prove that you're able to do that. And so what you do is, really what this comes down to is you're exchanging, you're passing integral signs in front of each other. And in order to do that, you need Fubini's theorem, because Fubini's theorem allows you to do that if the functions are measurable, and they also have to be finite. Like if you take the integral of the absolute value, then it needs to give you a finite number. So let's go ahead. Typically in numerical analysis, the functions that we're working with are super nice, so we don't have to really worry about this stuff, where you can like get by without worrying about it. But I think it is important to keep in mind, and I think this is sort of like a also a good way if you don't know a lot of measure theory or haven't seen a lot of measure theory. This is sort of a reason why measure theory is important, because it allows you to rigorously prove that you're able to do these things that you want to be able to do. So what we're proving is we're rigorously justifying this equation here, where we move this integrand inside the summations. Moving it past the etas is fine, because these etas, these are just numbers. And we know that integration passes through scalars. It's passing through the summations that's trickier. But anyways, what ends up happening is, so if you look at this function, phi prime of x and phi j prime of x, and you think of this as a function of I, j, and x. And so this will be x, this will be I, this will be j. So we're thinking of this as a function in 3 variables, and so therefore it is a function where you are going from the direct product of 3 measure spaces into the real numbers. And so it needs to be measurable, i.e. the inverse image of any measurable set on the real lines needs to be measurable in this product space. But that is sort of obvious, because what are the phi primes? The phi i's are hat functions, and so like a phi. So let's see here, if you've got these 3 points and phi I looks like this, then if you look at what phi I prime will look like, well, on the first interval it's sloped upward, so it's like this, and on the bottom interval it's sloped downward, so it's like this. So basically, so this is phi I prime. So this is just a like a piecewise function. It's not continuous. You've got, it's like 0 over here, and you've got an open circle, then closed circle, closed circle. Oh, well, it doesn't really matter what happens at that point, because this is measure theory now, and sets of measure 0 don't matter at all. Oh wait, no, that should be open. But yeah, so you basically have these indicator functions. So it's like, so if this is xi, then phi prime. Well, I don't remember like what the slopes are off the top of my head. I could derive them quickly, but that's sort of, we're getting into things that aren't really important. What's important is that this is like you get this interval here and this interval here, and it's 0 everywhere else. So this is a really nice function, and so it's obviously going to be measurable. And this is a finite direct product of measurable functions, so it's going to be measurable. You do have to be careful when you talk about like countable direct sums and uncountable direct sums. That's where measure theory starts to get really, really weird, and also not really used that much, so you don't have to worry about that much. But in here, you need that, so this is measurable. It's also uniformly bounded, because if you look at these hat functions, there's finitely many of them, and so the derivatives can only get so high. There's like, for each phi I, you've got two different slopes, so you can have like two different possible values. So there's like, you get 2m possible different values for these phi primes, and so there's going to be a uniform bound on them. And so let's say that uniform bound is just the constant m. Then if we integrate this thing, then this is less than or equal to, let's see here, the eta I, eta j's, those come out. Then you've got these things, and you've got, okay, so what's going on here is, so m is the Lebesgue measure on the interval from 0 to 1, so the measure of that interval is just 1. Now for the sums, the reason we're actually using measure theory here is that we're thinking of those finite sums as integrals with respect to the counting measure, which we'll denote by nu, on the measure space I, which is just the set of indices from 1 to n. So then this sum from I equals 1 to m is actually just the integral over that set I with respect to the measure nu. So that's what's going on here. But anyway, so we take the integral of these things, and this is going to be less than or equal to whatever the maximum of these things are times the measures of these three spaces. And these three spaces happen to have finite measures. So one of these, like the interval from 0 to 1, that's the Lebesgue measure of 0, 1 here. And then we've got the measure of, the counting measure of I multiplied by itself. So you get nu I squared. And so this is just a product of, a finite product of finite numbers, and so it's finite. So anyways, because of that, you can exchange these integrands here. And so you start here and you end here. Okay, so that's how you rigorously justify this equation up here. So we've now proven that A is positive semi-definite. But we're not done yet. We've got to prove that A is actually positive definite. So what we got to prove is, okay, so suppose eta is not the 0 vector, then there exists, let's see here, what does eta look like? What are we trying to do here? We want to prove that this integral is strictly positive if eta is non-zero. So if we look at this v, if eta is non-zero, then v is non-zero, because whichever non-zero, because eta will contain some non-zero index, and that will be part of this sum here. So then v is not equal to 0 as well. But we end up taking v prime. Okay, so how do we do that? Let's see here. Okay, so say eta I is not equal to 0. Then eta I phi I prime. Phi I prime is not going to be 0. Well, some of these functions, the phi i's, some of them might be 0 at certain points, like phi I plus 3 will be 0. Well, wait, no, that doesn't make sense. So basically this is not going to be 0 because phi prime is going to be non-zero like on those two intervals where the slopes are being accounted for. Okay, so eta I phi prime is not 0. So let's see here. So you get eta tau. I think we're at a point where we can actually go through and do the necessary inequalities. So this is going to be less than or equal to, well, let's see here. Well, it's going to be less than or equal to whatever happens on... So this is not equal to 0 on the interval from hi minus 1 to, no, xi minus 1 to xi in particular. In fact, from xi minus 1 to xi plus 1, it's going to be non-zero, but that doesn't really matter. So anyways, so this integral is going to be, no, we want it this way. This is going to be greater than or equal to the integral from xi minus 1 to xi of v prime squared dx. But if we look at v prime, v prime is the sum of these things. And these things, because it's being squared, these are all going to be positive. So we'll... Let's see here. Oh, this is tough to do on the fly. Okay, let's see here. This is not hard. I don't know why I'm blanking here. But anyway, so it's greater than or equal to this. So the vi prime, let's see if we take these sums, this thing squared, I shouldn't need absolute value signs in here. I think I'm going to add them. I think I'm going to add in absolute value signs just to make this easier on me. So this is greater, here, I'll do it like this. This is greater than or equal to this, which is equal to this. And now I'm going to use this, I think. Right, because then this is going to be greater than or equal to, basically all we want here is we want eta I, so eta I squared, and then integral from xi minus 1 to xi of whatever phi prime squared dx. And let me just make sure that this all makes sense. So we're going from vi prime, and we're taking the absolute value of this thing, and we're just throwing out a whole bunch of stuff that we don't need. And that should work. Because if you're looking at this, decreasing the region that you're integrating over will decrease the integral, will decrease the value of this integral, and then throwing out some of these things will decrease it as well. So we have all these terms here, and we're taking the absolute value of all these terms, and we just throw out a whole bunch of them, and all we keep is just that particular ij that we needed to get this thing. So yeah, this works perfectly well. But now here, we know that we don't even need this. We don't even need this part. All we say is since phi I prime is not equal to 0 on the interval from xi minus 1 to xi, we get this thing, and then this fact comes into play here, because what we're going to do is this integral is going to be a positive number, and this is going to be a positive number, strictly positive, so it's strictly greater than 0. So if eta is a non-zero vector, then this inner product is going to be strictly greater than 0. So hence, A is positive definite. I'll write it over here. Right, because all we proved up here was that it's positive semi-definite, because we didn't prove that you plug in it, because up here it still wasn't clear, like maybe you find a special vector eta that you plug into here and you get 0. This would still satisfy this inequality, but what we really need to do is prove that this inequality holds precisely when, or this inequality here is strict if eta is non-zero. And so that's what we've done here. And so hence we have that A is positive definite. And despite the fact that I messed this up on the homework, I was able to fix this here. So yeah, sorry that you had to sort of watch me sort of work my way through that on the fly. But yeah, we've figured it out, and that's the end of the problem.